Welcome to Coffee and Astronomy with Jim Craig. This is the first in what I hope to be a series of videos that I produce that help answer some questions that you might have about astronomy and space-related topics. Usually on Sundays, before we had the COVID shutdown and all of that, I'd get together on Sundays with friends and we'd sit and we'd have coffee and we'd discuss a lot of different things. But I can't do that right now, so until we can all get back together, I think this is a good way for me to help fill time and hopefully inform some folks. I'm going to ask you to stick around to the end of the video. I am going to make a plea to some of you folks. In an astronomy forum that I am a part of on one of the major social networks, I think you can figure out which one, somebody asked about UFOs. He didn't ask directly. What he did is he asked, in all of our viewing, if any of us had seen anything that was unusual or couldn't be explained. And some people were a little less than kind to him. I've tried to be fairly reasonable with him. And I said that I made videos like this, so I would make one that discussed this topic. And before I go on, one thing I should tell you about all of these coffee and astronomy videos is that they are unplanned. Well, they're not unplanned, but they are unscripted, unrehearsed, and unedited. So you're going to get this in the proverbial warts and all astronomy. So before I sat down to do this, I sat down and I did a little bit of math to try to figure out how to explain why I don't think we've ever been visited. And the first has to do with just the logistics of trying to send a spacecraft. Because our person did mention that human beings had gone to the moon, and we have. We went to the moon. We sent 9 different spacecraft to the moon, or 9 different missions to the moon. 6 of them landed. Apollo 8, Apollo 10, and Apollo 13 didn't land. We all know why Apollo 13 didn't land. Apollo 8 was just to get a spacecraft around the moon. Apollo 10 was to test the lunar module in orbit. And then Apollo 13, well, it had its problems. The Apollo spacecraft was really quite small, not much bigger than a minivan or a good-sized passenger van. In order to get a spacecraft that can sustain life for a reasonable amount of time, we had to get much bigger, and with that, we got the International Space Station. Well, using that as my baseline, I calculated how much energy it would take to move something the size of the International Space Station from here to the nearest star outside our solar system. The sun, of course, the closest star, but to the next star beyond our solar system. And that's Alpha Proxima, which is about 4.3 light years away. Now, convert light years into miles, you pretty much just multiply by 6. Then you tack on 12 more zeros. So we're talking about 25 trillion miles, which I then converted into kilometers, then converted into meters. Now, the time frame that we're looking at, we'd want to do this, if we sent somebody in their 20s, we would want them to be in their 40s or 50s when they arrived. So we'll just use the ballpark figure of 25 years. So you're going 25 trillion miles in 25 years, or about 1 trillion miles in every year. And I have some numbers that I wrote down here. The distance turns out to be 4.0 times 10 to the 16th meters, because we are going to do our math in meters. The amount of time, 25 years, is 7.9 times 10 to the 8th seconds. So we're looking at a velocity, because that's distance divided by time, your velocity. Your average velocity to get there in 25 years is 5.06. Sorry, I got a sneeze coming on. Is 5.06 times 10 to the 7th meters per second. That's pretty fast. That's 50 million meters per second. That gets us from here to the moon in roughly 6 seconds. So now that we have our velocity, we can figure out how much energy it would take to get a vehicle at that speed, or to that speed. And that's using, again, another mathematical formula for kinetic energy is, the energy is E equals 1/2 mv squared. So we have the v, the velocity. The m is for mass. So for mass, I looked up how much mass the International Space Station has, and it's about 4.21 times 10 to the fifth kilograms, or 421,000 kilograms. So we're going to plug those numbers into the formula. Yeah, the formula may appear up here, of 1/2 mv squared, and we're going to get a resultant energy of 5.39 times 10 to the 20th joules. That is a lot of energy. How much energy is it? It's about the amount of energy that the world consumed, the entire Earth consumed in 2010. So think of it. Every automobile, factory, aircraft, home air conditioner, everything. That's how much energy it would take to get this thing to Alpha Centauri, or Alpha Proxima, in 25 years. Now, even if that weren't an insurmountable problem, then you have the problem from that 25 years. The International Space Station is not self-contained. The International Space Station gets resupply missions on a regular basis. Well, you don't have something that can resupply. It has to be self-sustaining. That's going to mean a larger spacecraft. And that larger spacecraft, every pound is going to take more energy. Every kilogram is going to take more energy to get it moving. And of course, more energy means you have to have larger engines. Larger engines, more mass. There's a trade-off in it. That's why they stopped putting paint on the outside of the space shuttle toward the end of the missions. So if you watch the early missions of the space shuttle, the external tank is white. And then they stopped painting it because it saved 600 pounds of paint, and that was 600 pounds of payload they could take instead. Now, if you're paying millions of dollars per pound of payload, you'd rather have it be something useful than paint. But the International Space Station is moderately small, not self-sustaining, not self-contained. It does have to get resupply of oxygen, water, food, fuel to keep it moving or to keep it going in the proper attitude, all of those sorts of things. So the engineering is difficult at best. Now, you might suggest matter antimatter, which we have not contained enough antimatter to do this thing. But suppose somehow or another we magically find a way of generating antimatter that doesn't take more energy than you can produce with it, because on Earth right now, to get positrons, antimatters, or positrons are easy, I should say antiprotons, it takes more energy to produce an antiproton than you can get out of an antiproton. But it would take 3,000 kilograms of antimatter, or matter and antimatter combining together, so 1,500 kilograms of each, to hurl this thing. And think of the tremendous energy cost to produce that much antimatter. So, engineering-wise, unlikely. Not impossible, but unlikely. It requires a lot of suppositions. Well, what if we could do this? What if we could do this? What if we could do this? There is a principle in logic called Occam's Razor. And it pretty much says the explanation that requires the fewest presuppositions, the more likely that explanation is to be the right one. So we've already got, how can we, what if we could overcome this engineering? What if we could overcome the life support? What if we could, you have to come with a what if we a lot of times. Then there's the question of how would they know that we're here? Human beings, we transmit signals. I mean, I'm sending a signal to you in one way or another. And we've been doing it with radio for about 100 years, give or take a few years. Well, our radio signals have been expanding outward from Earth in an ever-expanding sphere at the speed of light, which means if we've been transmitting for 100 years at the speed of light, our signals are 100 light years away on either side. So we've got this sphere that's 200 light years across. And that seems like a lot of space until you realize that the Milky Way galaxy is 100,000 light years across. And I found a good analogy to sort of think of this. Imagine that you have a football field, only instead of being rectangular, it's square. And in the middle of that football field, you have a CD. Yeah, I picked this one. It seemed appropriate. Our signals have covered as much of that football field, or as much of our Milky Way, as that CD covers of our Milky Way. And in order to receive that signal, you have to be inside that little circle. Otherwise, you don't know the signal's there. It hasn't reached you yet. So the vast majority, 99.9% of the Milky Way galaxy, wouldn't even be aware of our radio signals. And the radio signals drop off over distance. It's an inverse square. If you take if you figure out how far it is from for 1 light year, if you go out 2 light years, it's 1/4 as much. The signal is going to be 1/4 as strong. Go out 3 light years, it's going to be 1/9 as strong, and so on and so on and so on. So by the time you get out to that 100 light year radius, you are at 1/10,000th the power that signal was at 1 light year. So even, it's unlikely that our signal could be received. Not impossible, but unlikely. So there's the supposition they could receive our signal. That assumes they can receive it. It also assumes they can interpret it, and they can figure out where it came from. The figuring out where it came from is probably pretty easy. It's the interpretation of it that's probably the biggest problem. There are other ways of knowing whether or not our planet has life. We can look at distant planets, because when I first got into astronomy, we didn't even know didn't know for a fact there were planets around other stars. But now we've actually detected thousands of planets around other stars. And we can, if this planet is positioned correctly, we can actually examine their atmospheres a little bit and figure out what's in the atmosphere. And life has certain chemical signatures to it. And one of those chemical signatures on Earth, something that would throw up a big red flag and say, there's life on this planet, is molecular oxygen. Oxygen likes to combine with other things. It combines with rocks. It combines with iron. That's how you get rust. A lot of different things have oxygen in them. But when oxygen bonds with oxygen, forming molecular oxygen, O2, the stuff that we breathe, that can only be produced one way in the quantities we see here on Earth, and that is living things, plants. When cyanobacteria first started photosynthesis, they would take carbon dioxide and water and combine them to get energy out, and the byproducts were sugars and oxygen. Our planet changed, and it made it possible for animal life to come about. In fact, it actually poisoned the environment for other certain microbes. The anaerobes were poisoned by the oxygen. So life has in the past changed. One final consideration on all of this is timescale. Our species has been technologically capable of communicating with the universe for about 100 years. But we also have been capable of leaving our planet for about 60 years. Will our time frame overlap the technological time frame of another species in another world? Now, I want to make it very clear. I hope that there is other life in the universe. I really do. I'd say the possibility of there being other life in the universe is very, very strong, because organic chemistry is easy. Well, relatively easy. Environments are plentiful. And we've seen here on Earth, even in some of the most unfriendly environments, we've seen signs of life. Is it intelligent life? Maybe. Again, I hope so. Has it come here to visit us? I'd say the chances of that happening are really, really slim. Razor slim. Well, if you enjoyed this video, I hope you'll click the like button down here somewhere. I don't have YouTube in front of me, so you can kind of guess where it is. But also down in the links, you're going to find a link to my Patreon page. If you become a patron, you can help keep these videos coming. You can help me make these videos. And if you're a patron, one thing that I don't accept, if you put a comment down here, I might consider answering your question. But if you become a patron, I will have a very good chance of answering any question that you have, or at least trying to find you an answer. Because, of course, the beginning of wisdom is no... Excuse me. That's why this is coffee. Coffee in astronomy. So I'm not coughing in astronomy. The beginning of wisdom is knowing when to say, I don't know. The beginning of knowledge is being willing to say, let's find out. But by helping me with my Patreon, you not only get help keep these videos coming, we also have videos for our Cool Astronomy Person of the Week that comes out every Monday, and my patrons get to see it a week before everybody else. I will answer questions, occasionally have prize drawings for people. It's either something I've created physically, or a drawing, or maybe a star chart, or we'll have to see exactly where that all goes. So consider for becoming a patron. It's $1 a month to start with. Get more, you have more perks for higher tiered memberships. So do consider becoming a patron. Also, hit subscribe, hit like, and let me know what you think in the comments. So until I see you again, I'm going to wish you ad astra to the stars, and have a great week.